I am R. Prabha, Assistant Professor in the Department of EC, SNS College of Technology. In this video, we will discuss the topic on arrays of non-uniform distribution. We know antenna arrays. In order to increase the directivity of the antenna, when a single antenna is not enough, we go for antenna arrays. Antenna arrays consist of more than one antennas oriented similarly to get greater directivity in a desired direction. So, a uniform distribution of the voltage in an array yields the maximum directivity, and the minor lobes are relatively large. The amplitude of first minor lobe is 24% of the major lobe maximum. So, in some applications, the minor lobe amplitude may be undesirably large. So, and also the pattern has a beam width of 23 degrees, but side lobes are relatively large. So, in order to overcome these disadvantages, we are going for a binomial array. So, binomial array is nothing but array of non-uniform amplitude, and as per the demand of modern communication, where narrow beam, that is no minor lobes, is preferred, it is greatest need to design an array of only main lobes, because the side lobe represents the power wastage in unwanted directions. So, the ratio of power density of main lobe to the power density of the longest minor lobe is termed as side lobe ratio. The particular technique used to reduce side lobe level is called tapering. So, in binomial array, since current amplitude in the sources of linear array is non-uniform, it is found that the minor lobes eliminated if the center element radiates more strongly than the other sources. Therefore, tapering need to be done from center of the radiator to the end to some specifications. So, the binomial array is common example of a tapering scheme, and also for non-uniform excitation. It is an array of n isotropic amplitudes and of sources and non-equal amplitudes. To reduce the side lobe level, John Stone proposed the sources have amplitude proportional to the coefficients of the binomial series of the form 1 plus x the whole power n is equal to 1 plus n minus 1 into x plus n minus 1 into n minus 2 by 2 factorial x cube plus n minus 1 into n minus 2 n minus 3 by 3 factorial x cube, etc. And here the n represents the number of radiating sources in an array. So, from this formula it is difficult to find the coefficients of the binomial array. So, a simplest method is to use Pascal's triangle. So, for an array of total length n lambda by 2, the relative current in the nth element from one end is given by Pascal triangle. For example, the relative amplitudes for the array of 1 to 10 sources are given in the diagram. For n is equal to 1, according to Pascal triangle, it is 1. For n equal to 2, it is 1, 1. N is equal to 3. The first element and last element is 1, and the second element is obtained by adding the previous row elements. So, 1 plus 1, previous row adjacent elements of the 2 is 1 plus 1 is 2. And similarly, n is equal to 4, it is 1. And the next amplitude is 1 plus 2, the previous row elements 3, and the next amplitude 2 plus 1 again 3, and the last one is 1. If we observe the Pascal triangle, the last elements, end elements of both the sides are always 1, and middle element is obtained by adding the previous row adjacent elements. And uniform array, secondary lobes appear, but principal lobe is sharp and narrow, where in Stone's binomial array, width of the beam widens but without secondary lobes. So, this is the disadvantage of binomial array. And first disadvantage, half power beam width increases but the directivity decreases, because for an ideal antenna the directivity should be high. So, this is one of the disadvantage of binomial array. And also, as the length of the array increases, large current amplitude ratio is required. For example, for n equal to 10 in this Pascal triangle, The first element is 1, the second element current ratio is 9, and the middle element current ratio is 126. So this is where the value is very higher. So for array length increases, the large current amplitude ratio is required. It is impossible. So this is about binomial array. And we have another technique called pattern multiplication to determine the radiation pattern of complicated arrays very rapidly just by inspection and not using any calculations. So according to the pattern multiplication technique, the total field pattern of an array of non-isotropic but similar point sources is the multiplication of the individual source pattern and the pattern of an array of isotropic point sources, each located at the phase center of individual source and having the same relative amplitude and phase. And similarly, the total phase pattern is the addition of phase pattern of the individual sources and the array of isotropic point sources. And this is the diagram of obtaining the 4 isotropic elements, the pattern multiplication technique. So according to this technique, the first 2 elements, the total array is divided into 2, and the one part is taken as the unit pattern, and the entire array is taken as the group pattern. By multiplying the unit pattern and group pattern, we get the total radiation pattern. Similarly, for 8 element antennas also, we can calculate the radiation pattern. So assessment. Pattern multiplication is the multiplication of single array radiation pattern with the answer is the direct array factor, and the second one is the excitation amplitudes of the binomial array follow. We know it is the Pascal strand. Thank you.